Hi, Assalamualaikum, and a very good morning, class. Okay, so today we will go through lecture for the chapter of effects of the atmosphere. Okay, let's see the contents of this chapter. So, uh, in the end of this chapter, students will able to describe the term extinction. Okay. After that, we have the refraction, seeing, scintillation, dispersion, and correcting for the atmosphere. Okay, so what is the Earth's atmosphere? Okay, it permits us to observe the distant universe only through a narrow window of the electromagnetic spectrum. So this following are the five distinct ways the atmosphere affect the light. Okay, from this source, that is extinction, refraction, seeing, scintillation, and dispersion. So the electromagnetic radiation from space, okay, could only look through to windows in the spectrum to learn about extraterrestrial sources. That is the optical, near infrared. The wavelength is around 3000 to 9000 angstrom. Radio 1 millimeter to 20 millimeter. So several windows of moderately high transmission continue through the infrared up to approximately 26 microns. Okay, Johnson U band was partly determined by the atmosphere ultraviolet cutoff, while other band passes in the optical are determined by the filter transmission curve. Okay, let's see what is the filter transmission curve after this. Okay, so this is the spectrum which range from zero point 0.1 nanometer to 1 kilometer range wavelength. Okay, so the y-axis is the atmospheric opacity, okay, in a percentage unit. Okay, so as you can see here, okay, so this is where you can observe or see the wavelength in this particular color. Okay, so basically it started from the full atmospheric opacity 100% until in the range of 100 nanometer to 1 micrometer, and after that it fluctuate and varies. Okay, and reach at a certain wavelength it like constantly 100% again, and after that it fluctuate to decrease and high. Okay, it become increment from 0 up to 100% after 10 meter, and then it is consistent again. Okay, so here is similar pattern we can see in their atmospheric opacity. So you can see what is the example of each different range. Okay, from here to here. Okay, at the below diagram you can see is a gamma rays, X-rays, and your ultraviolet light blocked by the upper atmosphere. Okay, best observed from space for this range. Okay, and after this after this range you can see the visible light observable from Earth with some atmospheric distortion. Okay, so it's distort right here, it's fluctuate. Okay, and then at the constant 100% atmospheric opacity, you can see the most of the infrared spectrum absorbed by atmospheric gas. Okay, best observed from space also. And then at this particular range, it is the radio wave observable from Earth, and after that the long wavelength radio wave block. Okay, at this range. Okay, so we go to the extinction. Okay, the infrared JHKLM system is determined by the narrow windows between the deep molecular absorption band. So the absorption in the infrared and submillimeter is caused mostly by water vapor. Okay, infrared and millimeter observations are made at high altitude mountain sites, which tend to be very dry and thus offer better transmission in these bands. Okay. Okay, so the Earth's atmosphere is not completely transparent in the optical sorry, in the optical particle of dust. Okay, droplets and molecules scatter and absorb light. Okay, as you can see here, is the ground and atmosphere, top of the atmosphere. So here is the zenith line, and when you see when the observer is right here, okay, when you is right here, you can see it, you see the sky or atmosphere at this particular angle. Okay, so actually you want to observe a star right here. So is the zenith angle to your line of angle, observe the star is actually is the Z angle and the second Z here. So basically you will see is not completely transparent in the optical, but you will pass through the dust, water, droplets, and molecules scatter and absorb the light. So the longer the light path, okay, this one is the light path, okay, the distance between the observer and the object that you want to observe. The greater is the atmospheric effect. Okay, so that is the atmospheric effect right here. Okay, so the dimmer the object will be. Okay, for example, sunset. Okay, the wavelength dependence of the absorption and scattering of light also causes the sun to appear redder at sunset. Okay, so the shorter wavelength, okay, you will see the blue light are more easily scattered than the longer wavelength, which is the red light. So starlight is also dim and reddened by the time it reaches the surface of the earth. This effect is known as the atmospheric extinction. So the atmospheric extinction of starlight depends on the altitude of the star, okay, above the horizon. So we can trace the effect if we make a series of the observation of the star at different altitude. For example, here is the observer. You have to if you want to know about the effect of the effect of the what we call that atmospheric extinction, you have to do observation at different altitude. Means if you stand here, maybe you will have to stand to another altitude, means another place or region sector to to know about the extinction. Okay, the atmospheric extinction. Okay, so the minimum pulse length of starlight through the atmosphere is for a star on the zenith, which we define the thickness of atmosphere as 1 air mass, okay, or X. So we have this particular formula here. So where X is basically the second Z is a good estimation for Z is less than 60 degree. And at 60 degree, x is equivalent to -2, and it increases rapidly for larger values of z. Okay, so if we plot the observed magnitude against ms for a star, okay, we find that points define a line, okay, define a line, and the slope is called the extinction coefficient. The slope means their gradient, okay, which is m. So m is equivalent to the extinction coefficient, where k is not constant every night and may even vary during the course of one night. Okay, so we have this Burgers law, m lambda equals to k lambda x plus m lambda or 0. Okay, where m lambda 0 is simply the y-intercept right here. Okay, this is the y-intercept or here. Okay, so here is the example of extinction plot. Okay, using real data measured with a CCD camera using the R band on the 24-inch telescope. Okay, so this is the extinction plot where you can see the decrement pattern here from 1 ms to almost 2 ms. Okay, it's about to decreases. Okay, a linear least square analysis. Okay, linear least square analysis will give you this value. Okay, since extinction depends on the wavelength, we can make observation through several filters to obtain a different extinction coefficient at each mean wavelength. Okay, so this one is the different extinction coefficient. Okay, at different each of their wavelength. So you will see here is 4,000, 6,000, 8,000, 10,000. So have a different variation of the k lambda. But basically it shows the decrement against the wavelength. The extinction is caused by the two phenomena, which is the absorption and scattering. So what is the absorption? Is the sorry, the destruction of a photon at a specific wavelength by an atom or molecule or even a range of wavelength by aerosol. Scattering is the redirection away from the line of sight of photon. Okay, both are talking about the photon. Okay, which is photons is referred to the light, right? So, for scattering, is the line redirection away from the line of sight of a photon by an atom, molecule, or a small aerosol particle. Okay, so what is aerosol? Okay, aerosol is a suspension of fine solid particles or liquid droplets in air. The steep, the steep rise in extinction at short wavelength, okay, results from Rayleigh scattering, which produces a lambda power of -4 dependence. Okay, the extinction curve level off at radio wavelength where aerosol scattering and absorption dominate over Rayleigh scattering. Okay, so what is volcanic eruption? Can inject aerosols, okay, into atmosphere that can remain suspended for months or even years. So what is the true color index CO? Okay, is the color as measured by an observer outside the atmosphere. So we call that is the true color index. So the true color index formula is equals to B naught minus V naught or equals to B minus V minus KBX plus KVX and so on. Okay, if we let Kc, okay, here, we let Kc be the difference between the two coefficients. So you will get C naught equals to C minus Kcx. Okay, so the equation for C naught, however, is not quite correct because it is found that atmospheric extinction also depends on the color of the star. Okay, so now it is observed. Okay, now here we have the blue object which fade faster as they approach the horizon. Okay, compared to the red object. Okay, so this means that the K measure, okay, the K measured for blue are different from red in any filter. Okay, so there is a K dependence here for both color of star. So a correction to the extinction coefficient is therefore required. Okay, due to the fact that stars with shorter wavelength suffer more extinction than stars with longer wavelength within the same filter. So, as stated in the previous slide, that which one is the long, um, which one is the long wavelength, blue star or red star? Okay, you can review in the previous lecture. So this correction is known as the second order extinction, and it can be understood by separating the extinction coefficient into its first order, K prime, and second order. So this one is the formula to relate it. Okay, therefore we have V naught or V naught. Okay, and this one. So the second order extinction is prominent in U and B bands, but negligible in V, R, and I bands. Okay, so let's see for the B minus V color index, you will get value of about negative 0.04. Okay, so how we determine the K prime, K double prime, which is what is the K double prime? Is the second order extinction. Okay, determined from a series of observation of a close pair of stars of differing color. For example, we have Albireo or B Chai apa. Uh, yeah, it depends on you what you want to um read this term. Okay, Beta Cygni, which has a bright yellow and faint blue star. Okay, so if you have this M1, M2, okay, the average of M1 minus M2, two colors here, okay, two stars. Okay, for C also, C1 minus C2 can recorded as both stars move from the horizon to the zenith, and it can be shown that we can get a similar equation as the Vogler's law, okay, here, where this K prime, double prime B is will be the slope of the graph. Okay, the slope of the graph means the M gradient. Okay, so actually you need two filters to do this calculation of C. Okay, so basically you have two filters. Okay, so the typical range of values for K prime V is between this value, magnitudes per ms, and this variation can happen throughout a period of 24 hours. So the values of K double prime for B minus V varies between this value, magnitude per ms. When starlight enters the Earth's atmosphere, we expect the east direction to be altered by refraction, since the atmosphere is denser than interstellar space. Okay, so recall from Snell's law, n1 sine theta 1 equals to n2 sine theta 2. We should expect stars appear higher in the sky than they otherwise would. Okay. Okay, so for the correction for refraction is required if once to measure the altitude of the celestial poles. However, the analysis of atmospheric refraction is somewhat complex because the density of atmosphere is not uniform or is not equal. Okay, so at mean sea level, the average atmospheric pressure is 760 millimeter Hg, okay, or Pascal, known as the standard atmosphere, okay, at ATM, the units. So this pressure decreases rapidly with increasing height. It decreases to 0.25 atm at a height 11 km, and this pressure at 50 km. So it shows the pressure decreases rapidly with increasing height. Okay, so since the refractive index of air changes with pressure, okay, so the refractive index is N. Okay, so N is change with pressure. So the actual path of a ray passing through the atmosphere should be a curve. Okay, due to atmospheric refraction, low objects appear to be lifted more than higher ones, and the difference increases rapidly as one approaches the horizon. Okay, for example, when you have the sun is very near the horizon, okay, it appears to be flattened, and we continue to see it when it is above 0.5 degree below our geometrical horizon. Assuming that the atmosphere is composed of discrete plane parallel layers increasing in density downward, we can apply Snell's law at successive boundaries between layers. Okay, so this is the effect of many layer. Okay, if the lowest layer, okay, were the only one. Okay, now we have the angle of refraction. Theta r is equal to C1 tangent ZA, where C1 is a constant and ZA is the apparent zenith distance. Okay, so if you have larger values of ZA here, okay, if you have a larger value, the curvature of the Earth's surface begins to become significant. Okay, so this is the formula. Okay, so C1 C2 is constant, depend on temperature and air pressure. Okay, so the equation works well for ZA less than 75 degree. Okay, so for the previous equation were derived theoretically, but we may also approach the problem experimentally. Okay, so for example, we have the Comstock formula. Here, here is obtained from the experimental. Okay, where P is the barometric pressure and T is the temperature. So defining sunset as the time when the upper limb, okay, upper limb of the sun, dia punya, this is your sun, right? So the upper limb means dia punya here. Kalau bahasa Melayu dia, we call that pinggiran. Okay, so limb is dia punya hujung ni. Okay, the above surface of the sun disappears below the horizon. The true zenith distance of the sun's upper limb is actually 90 degree at the moment of the sunset. Okay, so the day is therefore lengthened by the time required for the sun to move through this extra angle of altitude. Okay, so especially at high latitudes where the day may be lengthened by many minutes. So this is the differential refraction, the gradient in refraction over a range in zenith distance. So you can see here the difference when there's no refraction in this solid line, and where you have refraction taken into account, okay, for the dotted line. Okay, so this is the for the differential refraction. Okay, occurs because refraction increases so rapidly with zenith distance near the horizon that the lower limb of the sun is refracted much more than the upper limb. Okay, so this is the effect. Okay, is much smaller near the zenith, but is measurable across the small FOV of the typical telescope. So you have here the overall effect of refraction, okay, can be visualized as the lifting of all objects toward the zenith, okay, which in turn would affect the right ascension and declination there. For example, if you have a star S, okay, star S, and it's refracted, okay, we see the star S is at here S prime, okay, but it shows a change in alpha, that is ds prime, okay, and ds here, ds prime and ds, that is their refracted position, which can be solved by converting the coordinates. So this is the ways, okay, to solve this matter by converting the coordinates. Okay, so next we go to parallactic angle Q. Okay, this one. So what is Q? Is the angle formed at a point on the sky between a grid circle. Okay, this one is a grid circle or the hemisphere itself, between the point and the zenith, and a grid circle between the point and the celestial pole. So this one is a formula where you can get the parallactic angle, okay, where phi is the latitude, h hour angle, and zenith distance. Okay, so here is the parallactic angle plot. Okay, is a zero on the meridian here. Only at the north and south poles is the parallactic angle zero for all objects at all times. Okay, so you can use to calculate the field rotation also for instrument mounted on altitude azimuth telescope. Okay, okay. Before we go to seeing, okay, I think we stop here. Okay, for this lecture, we'll continue to the next lecture. Okay, thank you. See you again.